Hello everyone, welcome back to another mixed bag. If you haven't checked out the first one, make sure to look up to it. The link is in the description below. It is quite more important compared to this one. In this one, we'll be covering local minima and maxima and the very important translations and dilations. So let's dive right in. I have local minimums and maximums over here, and I cannot guarantee that they will ask you this on the test, unlike many other topics that I've taught. Nonetheless, you should know what is a local minimum or what is a local maximum. So it is a point that looks like it is either the top or bottom of a hill. More formally, where a polynomial function switches between increasing and decreasing. Now, concerning your AP Precalculus course, this is the definition you need to stick to. When you take AP Calculus later on, you'll have a more better and refined definition for a local minimum and maximum. Over here, we just know that it's a point where the function changes between increasing and decreasing, or in a layman's language, it is either the peak or the valley. So over here, this is a peak, this is a valley, this is a peak, this is a valley. And the only difference between a local maximum and a global maximum is that the global maximum is the highest of all local maximums, and the global minimum is the lowest of all global minimums. Since we do not have the entire picture of the graph here, we know this is the global maximum and this is the global minimum. So if we were to approximate the curve, I could do something like this. Okay, over here, you'll notice we have a local maximum here, a local maximum here. It changes between increasing and decreasing at these points, over here, over here. If you notice carefully, you increase here in this interval, and then in this interval, you come down. So this is a local maximum. But understand that none of them are higher than the global maximum, since it is supposed to be the highest point. And when we compare this to a local minimum, you'll have a local minimum here, you'll have a local minimum here and here as well. But again, none of them are lower than the global minimum because it is supposed to be the lowest of the minimums. So that was about local maximum and minimums, and I don't think there's anything else you need to know. Moving ahead, we dive into transformations. Now, I know this slide might seem a bit new right now. You might have not seen anything like this before. You have y is equal to a times f times b times x plus c plus d, and you have a bunch of new terms. I will go through each one of them individually, and then when we come back here, I'm going to explain you the main part or the thing that actually will help you understand this better. So I'll first cover each of them individually, and I'll come back to this slide again. The first one is vertical translations. It says that adding a number k to a function shifts the graph up if k is positive and shifts it down if k is negative. The function g of x is equal to f of x plus k is an additive transformation of the function f of x that results in a vertical transformation of the graph of f by k units. And I'm going to show you an illustration here. It just says that if you have a function f of x and you add a k, then the graph is shifted upwards if k is positive and shifted downwards if k is negative. If we have a look at the illustration, you see that you have a graph f of x is equal to x square. Yep, f of x is equal to x square. This is your original graph that I'm trying to highlight here. And when you add 3 to it, x squared plus 3, you get g of x. So you'll notice that each point is translated 3 units up. The point right here, I'm going to choose a different color. The point right here becomes this one, 3 places up. If I choose the point right here, 1, 2, and 3 units up over here. If I choose this point, 1, 2, 3, 3 places up. So the entire idea of the graph remains the same. The actual curve of the graph is still defined by x squared, but you shifted k units up where k is 3 this time. So the graph is shifted up. If k were to be negative, if we were to have x squared minus 3, then this thing would go, each of these points would correspond to 3 points down. So this would be here, this would go somewhere down, and something like that. I hope you get the idea. Now, if you understood the previous topic quite well, this will not be as hard as it was. We have the horizontal translations in which instead of moving up and down, the graph now moves from left to right. It says that subtracting a number h, I'm underlining this word, subtracting a number h from x in a function shifts the graph to the right if h is positive and to the left if h is negative. The function f of x, the function g of x is equal to f of x plus h is an additive transformation of the function f of x that results in a horizontal movement of the graph of f by minus h units. Now, minus h is not a typing error if you're assuming it to be a typing error, and subtracting here is a keyword that you need to look up to. Now, the only difference between a vertical and horizontal translation is that in a vertical one, you add a constant to the output. In that case, we had adding k to the output, which is vertical movement. But in a horizontal one, you add a constant to the input instead of the output. That is the main difference between the two. And again, quite similar to the vertical one, if h is positive, then we have moving to the right. And if h is negative, we have moving to the left. Now, before you take this in mind, I want you to know that whenever I give you f of x plus h, you first take out the h as it is, okay? You take out your h term with the sign. So if you have an f of x minus h, you take out the minus h, or if you have a positive h, you take out the positive h. And I want you to multiply the entire thing by negative sign. Since we have by negative h units, you multiply this by negative sign. So in this case, I'll have a positive h, and in this case, I'll have a negative h. So whenever I have a negative h, I have f of x minus h. The first thing would be to multiply the h along with the sign with a negative sign to get positive h. And if I have a positive h already, when multiplied with a negative would result in a negative h. And then you'd consider the sign to apply the changes, whether it will move right or left. And it will be much clearer with the illustration that follows. Now here is the illustration in front of you. Over here, the original graph is this one, which is f of x is equal to modulus of x. Now, a modulus of x is just returning the positive output. So if I tell you modulus of negative 7, that would be 7. If I tell you modulus of negative 1.3, that would be 1.3. If I ask you the modulus of 4, that would be 4. And the g of x that we have here in the dotted line is the transformation one. Now, if you notice, each and every point is moved by 3 units to the left. 1, 2, 3 to the left. 1, 2, 3 to the left. Even over here, 1, 2, 3 to the left. And so you know that the magnitude of h, or the transformation variable, will be 3. So if I try to work with what I will have, g of x is equal to the modulus. Obviously, you'll keep the modulus of x. No, I do not know the sign of h, and I know the magnitude of h, so I'll write a 3 here, and we'll have to think about the sign, which is something very important. Now, what one might do is that he or she might notice the graph moving to the left and immediately put a negative sign, modulus of x minus 3. But remember, I told you, whenever you're translating horizontally, you multiply it with negative 1 or a negative sign, and then analyze the movement of the graph. In this case, I want a movement to the left. I'll change my color. A movement to the left implies a negative sign of h, and since I know that I'll multiply whatever I have with a negative sign, I want to multiply this with something that would give me a negative sign, and that would obviously be positive h, because if I multiply it with a negative h, it would become positive. So I multiply my negative sign with a positive h to ensure that my movement is to the left, which is ensured by negative h. So whenever you're filling the sign here, notice that it is modulus of x plus 3 and not x minus 3. In this case, I'll make it clear once again. H is 3 over here. This is your h. You multiply it with a negative sign to get negative 3. And if h is negative, then it is moving to the left. In this case, it does move to the left. So your final function g of x would be modulus of x plus 3. We now move on to vertical dilations. Multiply a positive number a by a function where a is obviously not 0, vertically stretches or compresses the graph of the function by a factor of a. Over here we have three cases where, depending on the magnitude of a, we decide how the graph changes. So if a is greater than 1, then the points of the function move farther away from the x-axis. If a lies between 0 and 1, the points of the function move closer to the x-axis. And if a is less than 0, which means a is negative, then the transformation involves a reflection over the x-axis. I'll show you the illustrations right here. Okay, right here we have two broad cases. The original function in both of them is f of x is equal to x squared, which is quite convenient to work with. Now, in the first case over here, in the first picture, the new function g of x is equal to 2x squared. G of x is equal to 2x squared. Now, if you notice, each point in the f of x, I'll change my ink. Each point over here, or on the original graph, is moving away from the x-axis. This is moving away. It is moving in an upward direction from the x-axis, moving away from where it was, and that too not directly by a factor of like plus 2 like we had in translations, or negative 2 in translations. It multiplies it by 2, and that is how they work. So if I have a point, say here 1, then 1 will be multiplied by 2 to have 2. If I take this point 4 right here, then it will correspond to an 8 all the way right up there, which we can't see right now. So that is how it works. In this case, we know a was greater than 1, so it moved away from the x-axis. If a was, let's say, between 0 and 1, then the function would have been something like this, you know, moving closer to the x-axis. All the points, they're moving closer to what they were. They're moving closer to the x-axis. And that was for a being between 0 and 1. Like instead of a 2, we had a 1 by 2x squared. And for the second case here, whenever you're having a negative sign in front of the x squared, it said that you reflect it over the x-axis. But you not only reflect, you also compress or expand it as required, and then you reflect. So over here, the new graph g of x, or I of x as they state, is negative 3x squared. Negative 3x squared, which means every point is now 3 times closer, pardon, 3 times far away from the x-axis. So if I reflect this back again, I'll have something like this. It is not accurate. But if you notice the point 1, or not that point 1, this point 1 here is now 3 times farther away from 3. This point 1 is now 3 times farther away over here. And once you move it far away from the x-axis, you take the negative sign into consideration to just flip it over. Now, I know you might have a hard time understanding them because I myself am not very confident with these transformations. So it might be, or the explanation might be a bit unclear from my side. So you can ask me for any, clarifications if you need. Now, finally, we move on to the last transformation, which is a horizontal dilation. Multiply positive number b to x in a function, where again b is not zero. Horizontally stretches or compresses the graph of the function by a factor of 1 over b. Now, if b is greater than 1, the points of the function move closer to the y-axis. If b is between 0 and 1, the points of the function move farther away from the y-axis. And if b is less than 0, which means if b is negative, then the transformation involves a reflection over the y-axis along with the compression and stretching. And again, if b is 1, then there will be no change, and if b is 0, then we will not have a well-defined function. I'll move on to the illustration. In the first example, or in both of the examples, the parent function is f of x is equal to x cubed. Now, in the first example, the new function after the transformation g of x is 2x whole to the power 3. Now, understand that I'm not multiplying 2 with x cubed. I'm multiplying 2 times x whole to the power 3 to get 8x cubed. That is the difference between a vertical and horizontal dilation. In one of them, we multiply the output, which in this case would be 2x cubed. But when it's a horizontal one, I give you 8x cubed, in which I multiply 2 with the input. And as you can see, all the points, they move close towards the y-axis, even at the bottom as well. In the second example, the parent function again is f of x is equal to x cubed, but the I of x, which is the new function in this case, is equal to negative 2x whole to the power 3, which will be negative 8x cubed. Over here, the sign is negative. So once you actually bring the points closer to the y-axis, before the reflection, the graph would be something like this. So it is just the same as this one, but once you're done with that, you take it and flip it over the y-axis to get negative 8x cubed. Time for the final lap where we go through all four of them. Now that I know that we're comfortable with what is a vertical and horizontal dilation and translation, I'll quickly go through a few tiny tweaks and the general notation. So whenever you want to represent all the combinations together, you have y is equal to a times, and I'll denote the original function like this, f of, I'll stick to green again. Now, a times f of b times x plus c, bracket close, plus t. Now, notice one thing. Whenever you play with the input, okay, whenever you play with the input, whether you add or multiply, it will be something horizontal, okay. Whatever you do with the input, it will always be horizontal. Whatever you do with the output, whether it's multiply, add, it will be vertical. I'm giving you tips to remember how these things work. So whenever it's done with the input, it will be horizontal. Whenever it's done with the output, it will be vertical. Now, whenever you multiply, it will always be a dilation. And whenever you add, it will always be a translation. Okay, these are the four things that you should know. Input horizontal, output vertical, multiply dilation, add translation. And then you can obviously and very quickly recognize which is what. For example, if I ask you what is C in this case without looking at this part, and then you'll see, okay, it's something happening with the input, so it must be horizontal. And it is an addition, so it's a translation. So C is a horizontal translation. And if you look back over here, it is indeed a horizontal translation. Similarly, you can figure out the values of D, C, B, and A, and you'll be quite clear with them. Now, I again tell you that this is a tough concept, and I'm in 10th grade right now, and I still don't understand this quite very well. I'm referring to a book and teaching you this. So, yeah, you might face a few difficulties, but let me know in the comment section if you need any more helps or another video on this. Thank you.